Welcome back. In the last module, we discussed about interpreting various sizing requirements and how to derive about IOPS or CPU requirements, memory requirements, network bandwidth requirements, etc. In this module, we are going to see basically an example through a database AWR miner report. So that is an output from AWR data, and it provides a graphical insight from data collected from AWR performance views. So once you run AWR miner utility against any database, that output can be used with AWR miner utility, and that plots a graphical report for the database. So we will navigate through each sections of AWR miner report to understand the sizing interpretation. So let's take a look at output for one of the database. In the first row, the output shows the name of database, how many nodes it runs on, the platform of the database. In this case, it's a HPUX Titanium platform. The version of database, which is 11.204, how many sockets the physical hardware has, how many cores it has, as well as any virtual threads, total memory available on the system, and the days shows this is 30 days. So while running, it has captured performance data for 30 days, which is default for AWR miner. And then in the second row, it is highlighting you all of the peak values for the stats, like CPU utilization. It shows 98% that is used for this time frame. Read IOPS is shown here, write IOPS is shown here, read MB per second, write MB per second, how many logons per core or number of SQL executions per second, commits, average active sessions, system global area, program global area, or database size, which is showing up 80 terabyte roughly. So these are very important stats, and the advantage of using AWR miner is it provides you all of them in form of a graphical chart. So not necessarily like these values are to be considered for sizing, but these are the peak values, and the further sections explains the average values which is shown there, and we would be able to drill down into all of these matrices in this report. So the very first chart is average active sessions by weight class, and we have understood what exactly is average active sessions. So it is DB time over elapsed time, and the left hand side the chart shows that the colors represents the database time here. So one of the observation is the CPU cluster. CPU is taking up 50%. It is contributed towards average active session, whereas cluster weights is contributing 19%, or user IO is contributing to 17%. And on the right hand side, we have further classification of these weight classes. So the first thing is like archiver weight on send request, or DB-CPU, or DB file sequential reads. So the goal for us is to identify how much is the average active session, which is coming from AWR data. And average active sessions is showing up 817, which is definitely way higher than the number of cores present on the system. So looks like based on this one, it could be a CPU bound system, but as I said, like these values are the peak values, so not necessarily the actual representation of the required resources on the system. So we'll further drill down and see what it shows in terms of average active sessions. So the second so here it explains, basically it's a funnel chart, and for all of the important parameters like average active sessions or CPU or read IOPS, read MBs, you have a funnel chart here. And what we need to consider here is like where this funnel is ending. So there are definitely some outliers which is shown in this orange color, but we can see the funnel is ending roughly here, which shows roughly 40%, or basically 40 as average active sessions on a regular basis. But these are the outliers, and sometimes it has even reached 400, but that not necessarily giving us that that is the requirement for sizing the CPU. So CPU, on the other hand, roughly 40 we can consider, because funnel is ending over here. The average values are 18.2 here. These all in red color shows the average values, which is there on the system. So same for number of executions for read IOPS. We see it is roughly average in range of 34,745, but it reaches to 100,000 here. And read MB per second is also less than 5,000 MBs per second, so less than 5 GB. But this gives a clear idea on what can be considered from an average utilization point. Number of sessions is roughly 3,000 user sessions which are connected to this database. The write IOPS is shown here, like that is roughly 30,000 write IOPS, that is on an average, but it is reaching up to 120,000. Write MB per second is roughly 277 MB per second, but safely you can assume at least 2.5 GB per second on an average. So important parameters are average active sessions, CPU utilization, IOPS, and MB per second, along with the outliers here. For the graph like shows the average active session distribution for the time frame. So this data is for December 27 to Jan 28, and it shows the behavior of average active sessions. So all these green colors, you can see 163 or here 491. So that is the average active sessions. There are one of cases where it has reached probably 1800. So not necessarily this indicator of the normal requirements, but it could be a problem window within the database system. So average active sessions is DB time over elapsed time, and it shows how busy is database system and represents the sum of active sessions over all sessions at any given point in time. The next chart explains the OS CPU as well as database CPU for the database. So you have to look for operating system CPU utilization against number of CPU present to get fair idea on CPU utilization behavior across AWR retention period. So out of these, like these three nodes, these are three database nodes, and you see database CPU as well as operating system CPU, and these are roughly in range of 30s or 40s maximum for database CPUs, and in red color it is the operating system CPU. So that is also shown here across all these databases. So in case of Exabase, target CPU percentage would be less, as most of the SQL processing happens at a storage cell. As a result, more consolidation density. This chart shows the IO average and max IO of the database, and read IOPS, as we already discussed, can be calculated from here, because you know how much read IOPS is and how much read MBs per second, or write IOPS as well as write MB per second. So we can calculate those data easily for our sizing. This is segment activity for the database, and it shows the growth of database across indexes or large objects or tables. So that gives a future perspective also, how much data we are adding every day here, that is GB added, and then how much logical reads we are doing, or physical reads we are doing, or physical writes we are doing. So that provides inputs for our IOPS requirements. Again, this is another chart like which shows you IO characteristics. So IO request by size, and these large read IOPS or large write IOPS or small reads or small write IOPS, they help you understand the workload behavior. For a transactional system, it is going to be more of a small reads or a small writes, versus for a decision support system, you will have large read IOPS or large write IOPS. This is the IO wait event histogram, and it shows distribution against like DB file scattered read or sequential read, log file parallel writes, and log file sync. And even DB file scattered read is typically used when fetching blocks for a full table scan index, fast full scan, and also performs a multi-block IOs. DB file sequential read, on the other hand, is a single block read, and it is typically engaged for any activity where multi-block IO is unavailable. And based on this chart, we see that like most of the requests, like, for example, here more than almost 90% of the request is getting served within a millisecond. Even for in case of the file sequential reads, majority 97% is served within a millisecond. Log file parallel write, everything is almost in 1 millisecond. So definitely IO subsystem is not a bottleneck here in this system. Log file sync activity is getting done in less than a millisecond. In case like if you have a problem, you will see like it is going from 8 millisecond or 60 millisecond and above. So they represents the poor performance within IO subsystem. This chart is average active session distribution by day and the hour, and during daytime 8 a.m. to 8 p.m. versus nighttime, how database is behaving. So this all represents the database time, and we can see that the workload is a kind of mixed workload, I can say, because activity is mostly in daytime it's more busy, but in nighttime also a lot of activities are happening within the system. And it could be you can also make a guess that maybe reporting or kind of analytics is running during the night time here. Some other variables which is shown here is like how many commits or execution per second or any kind of hard parses or log on behavior. Redo MB per second, that is another important point to consider. And you can also calculate the network bandwidth from these data. So required bandwidth is normally redo generation bytes per second divided by 0.7 into 8 and divided by this particular number, and that provides bandwidth in Mbps. So think of like if your redo generation is 1943, that you can find from your AWR reports or this particular data. So in that case, it can translates to this 0.022 Mbps from your AWR redo bytes per second is taken. Normally redo generation in a typical application would be 20 MB to 100 MB per second. In a high bash systems, it could be 200 to 300 MB per second, and this is what we see here. So required network bandwidth can be calculated from here, and 20 MB translates to a 240 megabyte per second as a network bandwidth. In case of a real application cluster, you have cluster related weights, and you need to factor the GC related weights for cluster databases. Another thing to keep in mind is Exa database system can have very low latency, InfiniBands in place, and they provide Exa fusion, so that can greatly reduce these particular weight events if that's the bottleneck in the system. This is about the memory stats, and it shows you how much total memory is used, SGA as well as PGA, and that can help for your sizing the required shape or system. Another thing to keep in mind is on Linux based systems, since on Oracle Cloud Infrastructure we provide all the databases on Linux platform, so you need to have use large pages as true. So most of the databases when they get provisioned, they come up with these best practices like use large pages are true, or you can also take a look at how much is the value for huge pages, because huge pages is something like can be calculated based on how much SGA requirements you have. It also shows the SQL percentage by schema and type, and this is more useful to derive the schema based consolidation or PDV approach, and also helps with defining resource manager or CPU or IORM plans within the database. So it shows the activities like create indexes or select like is the most found activity in this particular database. Then who are the users, like who is contributing to so top 10 schemas are provided here. So here if an related user is contributing the most, and then we have audit related user here. This was the SQL characteristics, means you can know database queries behavior in terms of elapsed time by top schema user. So just to summarize, we have gone through AWR miner report output, and I explained how to get useful data from report for cloud migration, such as IOPS or memory or CPU sizing, network bandwidth, etc. The report also helped us understanding the database workload behavior in terms of OLTP or decision support system. So with all of this, the next module we are going to discuss is capacity planning, validating the cloud migration. Because now we know how to derive sizing for any new cloud migration, it is equally important to validate the cloud migration, and we need to do a unit testing as well as load testing of the database. And the tool we are going to discuss in the next module is real application testing that provides SQL performance analyzer as well as database replay. SQL performance analyzer helps with unit testing of SQLs, and database replay helps with load testing of SQLs. In addition, real application testing also provides database consolidation workbench, which is basically a very ideal tool for getting advice on any cloud migration. So next, I will see you in next module on how to validate the cloud migration.